we will start with quickly the discussion about power today, and then we will move on to doubts and questions from HC Verma and module, etc. Okay. So in the last few lectures, we have learned about the relationship between potential energy and internal conservative force and the work energy theorem, etc. So we will just start by understanding the last concept within this chapter, which is the concept of power, the last definition and concept. Okay. So power is defined as the rate of work done with respect to time. Okay, so for example, we define something called instantaneous power. P delivered by a force, let's say F. So that instantaneous power delivered by the force is defined as instantaneous rate of change of work done with respect to time. That is how we define the instantaneous power delivered by a force. So this becomes F dot ds by dt. So that also becomes F dot v, because you know that work done in a small time dt is defined as F dot ds. Okay. And rate of displacement with respect to time, the instantaneous rate of this thing, displacement with respect to time, is the instantaneous velocity. Okay, so ultimately the power which is defined as rate of work done with respect to time, it also becomes the dot product of force with respect to velocity. So the alternate definition of instantaneous power becomes that scalar product of or dot product of force with respect to velocity. Okay, where F is in newtons, V is in meters per second. Okay, so power is in what we call watts, where 1 watt is equal to 1 joule per second, or that's the same thing as 1 Newton meter per second. Okay, so this is the SI unit of power. We've discussed power in the last lecture, is it, Ayush? Okay, okay. So then we'll do some more examples. Just give me a moment. Yeah, we had just started with this in the last lecture. Good. Right, so we have understood instantaneous power. So we will proceed with the other definition of power also. So this we had seen in the last lecture. That's correct. Okay. We have already seen this definition in the last lecture, and you've seen the definition of British horsepower also. Okay, yeah, I will send it. Okay. Now the next thing we will see. So this particular definition we saw in the last lecture, the instantaneous power. Okay. Now related to this, the next definition we will see today is average power. Delivered by a force in a time interval delta t. Okay. So just like instantaneous power is defined as instantaneous rate of change, so average power is defined as the average rate of change, or the average rate of work done with respect to time. Instead of instantaneous rate of work done, it becomes average rate. So average power becomes total work done divided by total time. Okay, so it becomes integration of f dot ds, the whole thing divided by the time interval. So this thing is, yes, that is how the average power is defined. So this cannot be defined in terms of instantaneous velocity. Okay. This cannot be defined in terms of instantaneous velocity. However, if the force is constant, then this can be defined in terms of average velocity. But remember, that is only when the force is constant. Otherwise, we cannot define work done by this simple dot product. We have to define work done by integration. So this relation which I'm telling you, this one holds true only for force being a constant force. Okay, because S upon delta t is nothing but average velocity. Okay. So in general, this is the proper definition of average power. Okay. But specifically, it becomes dot product with average velocity provided the force is constant. Okay, so let's work out another quick question based on these. So this time we have this situation. We are firing a projectile, or a particle is fired into a projectile motion, okay, at t equal to 0. We are firing it at a speed u at an angle theta of projection with respect to the ground, and the mass of the particle is m. So a particle of mass, let's say 2 kilograms, okay, is projected at t equal to 0 at u equal to 25 meters per second, theta equal to 53 degrees as shown. Take the value of acceleration due to gravity to be 10 meters per second square. So G is acting like this, and find out the instantaneous power delivered by gravity at t equal to 1 second, t equal to 2 seconds, and t equal to 3 seconds. And next up, the average power delivered by mg again for t equal to 0 to 2 seconds, and secondly for t equal to 0 to 4 seconds. So just try this out. You have to just use these formulae that we've discussed above, that instantaneous power delivered by a force. I'll just show you the formula for reference. Instantaneous power is F dot V, whereas average power is total work done divided by total time. These formulae will be useful. Yeah, Ayush, I will scroll up again after a bit. Okay, just start working on this question and note down the data of the question first. Then I will take you back to the previous section. You can complete noting down. okay, so let's get started on this. So we have to do the vector analysis in this to understand, because for the first part now, we will be using the formula of instantaneous power as F dot B. So we'll need to calculate velocity in component notation so that we can take the dot product. So the force here we're talking about is of course mg. So its direction we'll take as minus j cap, because we will take our standard xy system of axis as the horizontal and vertical system. Okay. So rest is all using the projectile motion equations. So if you project a particle at an angle theta with respect to the horizontal like this, then at t equal to 0, the initial velocity we can write as u cos theta I cap plus u sin theta j cap. So that over here will become, because u is 25 meters per second and theta is 53 degrees, you will see that this becomes 20 I cap, sorry, 15 I cap plus 20 j cap. The x component is 15 and the y component is 20 respectively. So since the acceleration is this, so it's minus 10 j cap. Okay. So from this and this, you can see that as the particle is moving like this, at any instant of time t, its velocity vector changes to this, where the velocity becomes u cos theta remains constant along the x-axis, but along the y-axis it becomes u sin theta minus gt j cap. This is the property of projectile motion. So in this case, this will become 15 I cap plus 20 minus 10t j cap. So this is the velocity at time t, instantaneous velocity. So this is what we have to use over here. Yes, Kunj, very good. That's correct. Okay, so we will see that in the A part, at t equal to precisely 1 second, the instantaneous velocity is becoming 15 I cap plus 10 j cap in meters per second. And the force of gravity we are talking about is, remember the mass of the body was 2 kg. So the weight is of magnitude 20 newtons. Okay. So here we will substitute this as minus 20 j cap in newtons. So the instantaneous power, we have to just take the dot product of these two. So you will see that this becomes minus 200 watts at the instant t equal to 1 second. And this is the same exact calculation we have to repeat for the B part, and then again for the C part, 3 seconds. If you do that, you'll get the same, you'll get the correct answers for B and C. Kunj, your answers are correct for both of them. Now let me check your answers for the second part also. Yes, it's correct. Okay, now let's come to the second part where we are calculating average power. So for the second part, work done upon time. Okay, now remember mg is a constant force. So we can calculate work done as mg dot s. So the average power will become this, or you can even say that it will become mg dot average velocity. So in a projectile motion, you can again see that at any time t, the displacement is given by the sum of the x component and the y component. So that is 15t. So that is 20t minus 5t square. So now in the A part, from 0 to 2 seconds, you can see that the x component of displacement will be 30 and the y component of displacement will become 20. Okay. So the work done become minus 400 joules. So the average power will reduce to minus 200 watts. So this is the A part of this one. Okay. Yeah, I forgot we have to also work out the B and C part of this. So for the B part, at t equal to 2 seconds, you can see that the instantaneous velocity is just becoming 15 I cap. The y component is becoming 0. From this you can see. So the power is going to be 0 because velocity and force are perpendicular to each other. So at 2 seconds it is 0. And then again at 3 seconds, the instantaneous velocity from here, again you substitute and you'll see it becomes 15 I cap minus 10 j cap in meters per second. As the gravitational force is minus 20 j cap in newtons. So the power which is becomes plus 200 watts. So this is still the first part. Now this is the second part where we are talking about average power. Yes, Itanshu, that's good, correct. Okay. So the first part, the three answers are minus 200, 0 and plus 200 watts again. Okay, now let's come to the second part. The second part, the average power from 0 to 2 seconds, the answer will come out to be this much. It will come out to be minus 200 watts for this interval. Yeah, so Hitanshu, see what's happening in the second part. Now we have to calculate the average power. So the average power is defined as work done divided by, total work done divided by total time. So 0 to 2 seconds में मुझे work done निकालना है by mg. So work done will come from dot product formula because mg is a constant force. So firstly, I need to find the displacement from 0 to 2 seconds. So for displacement, I have the projectile motion equations, the x component of displacement and the y component of displacement. They are given by this. So now in this formula, I will substitute t equal to 2 seconds. So I'll get my x component of displacement and y component of displacement. So then the dot product of force with displacement will give me work done. And after work done, I will divide that by the time interval, which is 2 seconds. So work done divided by time will give me the average power. Is it clear now, Hitanshu? Now next we'll calculate the same thing for 0 to 4 seconds. Instead of 0 to 2 seconds, for 0 to 4 seconds. Yeah, just try it out yourself for 0 to 4 seconds. Kunj, your answer is correct. Yes, very good, beta. That's correct. Hitanshu, your answer is correct. Okay, so exactly the same method everybody else can also work out. So you will get at 4 seconds, you will get x coordinate is 60 meters, but more importantly, y coordinate is 0. So the displacement is only 60 I cap in this interval of time. So the work done by gravity will become 0 because they are perpendicular. No? The displacement is horizontal. So the work done is 0. That means the average power will also be 0. Okay, so this is a simple example. Now the final thing about power that we should understand is what about the net power? Now, if there are n number of forces acting on a particle or on a body, then we know how to calculate the instantaneous power by any one of them. But what about the net power? Let's understand that. So if multiple forces are acting on a particle, number of forces are acting, let's say, then power, that is instantaneous power, by each force. If that particle is having an instantaneous velocity v like this at that instant, is F1 dot v. The second force is delivering a power of F2 dot v. Like that, the nth force will deliver a power of Fn dot v. So the net power the summation of the power delivered by n forces. Okay. The net power becomes this. So you can see that it becomes F1 dot V plus F2 dot V addition up to the nth term. So with the distributive property of dot product, this can be written as the sum of all the forces dot product with velocity. And this is nothing but net force, not velocity. Okay. So the net power can be defined as the net force dot velocity. Now we'll see that this net force dot velocity also has a special significance. Okay. Because net force acting on the body is equal to mass into acceleration. Okay. And acceleration's dot product with velocity becomes acceleration's tangential component into velocity. So let me explain this point. If a particle is moving along some kind of curved path like this, okay, then at any instant, its velocity vector will be along the tangent. The velocity's vector is along the tangent to the curve at that point. And perpendicular to the tangent, you have the normal. In circular motion, this normal becomes a radial direction. Okay, but I'm talking about a general curved path. Okay. Now the acceleration vector, if it is like this, where this angle is theta, then E cos theta becomes what we call the tangential component of acceleration. Which we denote by et, and from circular motion you'll remember that that is equal to rate of change of speed, whereas A sine theta is what we call the radial component or the normal component of acceleration, and that becomes actually v square by r, where r is the radius of curvature. So this is the normal component of acceleration, okay, which basically becomes equal to v square by r because it is centripetal in nature. Okay. And r is the radius of curvature of the path. So here we don't need to worry about this because this part will not come into play. It is only the tangential acceleration which will come into play. Okay. So this is the general concept. Okay. Now coming back to what we are doing here. So if we are calculating the dot product, if we are calculating the dot product of acceleration and velocity, we can see that E dot V will become AV cos theta. So that can be written as V into E cos theta, which is nothing but V into tangential acceleration. And tangential acceleration itself is nothing but dV by dt. So E dot V becomes this. This is what we'll now substitute over here. So this dot product can be written as V into dV by dt because tangential acceleration is rate of change of speed. So now coming back here, the net power was this, which became this, which further became this, which is mv dv by dt. Okay, so now notice that if you differentiate the kinetic energy with respect to time, you will get the same term. It's half m into 2v into dv by dt. So it is mv dv by dt. Okay. So therefore, the net power equals to the rate of change of kinetic energy. So the net power delivered by all forces on a particle or body equals to the rate of change of its kinetic energy with respect to time. So this is the concept of net power, which is important. Okay. So I'll just minimize this a little. So make sure you understand all the terms over here. Okay, now there are some particular questions that I want to discuss. With this, we complete the theory aspect and all the concepts of this chapter, work by energy. So we will do more examples and questions. So let's start with this example that a particle of mass 1 kg moves along the x-axis in 1D motion, okay, under the action of a conserved given by F is equal to Cx square, where C is a constant. So if the value of C is 20 Newton per meter square, okay, and its potential energy at x equal to 0 is 0, then find the formula for its potential energy as a function of x, and B, if it has a kinetic energy of, sorry, if it has a speed of 2 meters per second at x equal to 1 meter, then find its speed at x equal to 0. The particle has a speed of 2 meters per second at x equal to 1 meter. Then what will be the speed of the particle when it comes to the point x equal to 0? Okay, so let's start with this question. Just try this out. Yeah, Kunj, I'm explaining both the parts actually. So basically, see, only conservative force is acting, na? So mechanical energy will get conserved. So once you get the formula for potential energy, na? So potential energy का formula हम कैसे निकालेंगे? We'll use this relation that delta U is negative of work done by internal conservative force. Okay, so this will be my internal conservative force. This one will be okay. So we'll substitute this here, and once we get this, here we'll use the relation that mechanical energy is conserved, because it has told us clearly that only a conservative force is acting on it. Okay, you can actually add the word only over here. So that means there is, okay, because external force is not there and non-conservative force is not there. So delta Ke plus delta U will be 0. So this concept we have to use. Just add the single term only over here. Okay. Under the action of a conservative force F given by Cx square only. Is it clear now, Kunj? Okay, good. Okay, so let's start with the first part. So we want to find the formula for potential energy. Okay, and given to us is that the conservative force is Cx square, that is 20x square, where C is 20. Okay, so this is the conservative force. And also given to us that the potential energy at x equal to 0 is 0. This information is also given to us. So using this now, we will find the formula for delta U as negative of work done by internal conservative force. So it's a one-dimensional system. So this will become minus f dx integration. Okay. So that is minus of 20x squared dx. So the change in potential energy, let's say U at some x minus U at x equal to 0 is equal to minus 20x squared dx integrated from x equal to 0 to x equal to x. This concept we use. This is nothing but this, that delta U is negative of work done by the internal conservative force. So this thing we want to calculate, U at x equal to x. This is given to us as 0. This is given to us as 0 here, as you can see. Okay. And on the other side, we have the integration, which is minus 20 x cubed by 3 from x equal to 0 to x equal to x. So the formula of our potential energy is becoming like this. It is minus 20 by 3 x cubed. Okay. So this is U as a function of x, the potential energy as a function of x, where the potential energy will be in joules. for x given in meters. Okay. Now, once we got this, for the B part, we can use the relation that change in kinetic energy plus change in potential energy should be 0. So, given that B is equal to 2 meters per second and the mass of the particle is 1 kg, we'll make the mass of the particle a little bit more, okay? Otherwise, I'll tell you why. So, we'll make the mass of the particle 4 kgs here. Okay, so now it is given to us that the speed of the particle is 2 meters per second at x equal to 1 meter. Okay. So V is equal to 2 meters per second at x equal to 1 meter. Okay. And the mass of the particle, I have changed it to 4 kg. So that means the kinetic energy is how much? It is 8 joules at x equal to 1 meter. And the potential energy formula we just seen. So potential energy is how much? It's minus 20 by 3 at x equal to 1 meter. So this is the value of kinetic energy and potential energy at x equal to 1 meter. Now we want to find out the kinetic energy at x equal to 0, where we know the potential energy at x equal to 0 is 0. Okay. So let's say this is my initial position and this is my final position. So now I'll use this data, this and this, for this theorem here. So we'll substitute this information here. The change in kinetic energy plus change in potential energy should be 0. So final kinetic energy minus initial kinetic energy plus final potential energy minus initial potential energy should be 0. So here this is my final position. So the final kinetic energy is unknown, but the initial kinetic energy was how much? 8 joules. Final potential energy is 0, but initial potential energy was minus 20 by 3. Okay. This is 0. So my kinetic energy is becoming 8 minus 20 by 3, or 8 minus 6.67, or you can say that is okay. So this is the kinetic energy at x equal to 1 sorry x equal to 0. So half mv square is equal to 1.33 joules, or more precisely that's 4 by 3 joules. So the speed, which is a magnitude quantity, so we won't take plus minus, is this. So this is the speed of the particle at x equal to 0. Okay, so I'll just scroll up first for the formula of potential energy again. Then the second part we'll see how we use that formula to apply in the work energy theorem and find the speed. Okay, so formula of potential energy, I hope is clear to all of you how the derivation has happened. Now, once you got the formula of potential energy, next is we are able to apply this conservation of energy, no? Conservation of mechanical energy. Why? Because there's no external force and non-conservative force doing work. Okay, so that's why we are able to apply the conservation of energy principle here. So change in kinetic energy plus change in potential energy should be 0. So now it is given to us that at x equal to 1 meter, the speed is 2 meters per second. So I know the kinetic energy, and from the formula I know the potential energy. Whereas at x equal to 0, I want to find out the kinetic energy, but again from the formula of potential energy, I know that u is 0. So I know delta u and delta k, I can calculate the sum of the change in kinetic plus change in potential has to be 0. So this is known to me, this is unknown. So I can find out the final kinetic energy from that. And that will give me that this is so much. The V is becoming square root of 2 by 3 meters per second. Okay, next up we will do very important question about the application of work done by energy theorem involving spring potential energy and work done by friction, etc. Those kind of things. Okay. So this example is actually a question in HC Verma. I'll tell you the question number in a moment, but just take down the question first. So there is this rough inclined plane, which is of inclination 37 degrees. And there is a spring attached at the bottom to a fixed wall kind of thing. There's a spring like this. And initially a block is released from this position here, A. Now the surface is rough. It has a coefficient of friction mu. The spring has a spring constant K. And the distance of the block from the tip of the spring, this distance is given to us as small d. Okay, the mass of the block is m. So now the data which is given to us in the question, just a moment, tell you the question number also. Yeah, so this is question number 43 in HC Verma. Work and energy chapter, question 43, the main exercise. Okay, so the given data is that the mass of the block is 2 kilograms and the distance d is 4.8 meters. Okay, so the block is released from the position A at rest, okay, slides down and compresses the spring by a maximum of 20 centimeters. So the maximum compression that the spring undergoes is 20 centimeters, and thereafter makes a displacement of 1 meter, makes a displacement of 1 meter up the incline. So basically, it sort of rebounds up the incline after. So it rebounds off the spring and makes a displacement of 1 meter up the incline. So from all this information, we have to find two unknown quantities, which is the coefficient of friction and the spring constant. Okay. Take the value of G as 10 meters per second square for this question. So we'll solve the question in detail. It's a very important and good question. But first of all, I want you to try and figure out how we will set up the work energy relation over here. How should we use work energy theorem? What should we take as a system, etc. And what all terms will be there in our work energy relation so that we can solve for these unknown quantities. Okay. So try to understand how we will apply work energy theorem over here and come up with some equations yourself so that we can find out the unknown quantities mu and k. Okay, I'll put up the solution in a minute. Okay, people, so let's figure out how to work out this question. So the first thing we'll do now, we will understand what we should take as a system before we can apply work energy. So our system should consist of the block plus the spring plus gravity, or basically the earth. Okay. So then what is happening? Spring force and mg, these are all internal conservative forces. Okay. The normal reaction is the external force, but the work done by normal reaction will be zero, because normal reaction acts on the block in this direction and the displacement is happening along this line. So they're perpendicular. Okay. So we don't have to worry about that. And friction, kinetic friction, is the non-conservative force. So work done by non-conservative force will be work done by friction. So our statement of work energy theorem for this will be that work done by friction is equal to change in kinetic energy plus change in gravitational potential energy plus change in the spring's elastic potential energy. This is the statement of the work energy theorem we'll have to solve. So now let's see how we're going to solve this. So first up, we will look at the state of the system from where the block started. Let's say the block started from here with initial speed at the point which we have designated as A. And this distance we have taken as D, 4.8 meters. This angle is 37 and all that. Now from here, next we will look at the system when the block compresses the spring to the maximum value. So when the spring is having maximum compression, that time let's say the block is against the spring like this. So if the natural length of the spring here was some L, now here it has become L minus X, where because it is a maximum compression, the speed of the block has become 0. So let's call this position B. Okay. So from position A, the displacement will be how much? The displacement of the block would have become D plus X. Okay. And it is given to us that X is equal to 20 centimeters when B is 0. That is the maximum compression state. So for the maximum compression state, this is becoming 4.8 plus 0.2 is becoming 5 meters. Okay. So first let us apply work energy theorem from A to B. So A to B, work done by friction will be change in kinetic energy plus change in elastic potential energy of the spring plus change in gravitational potential energy. Okay. Now while the block is moving downwards like this, friction is acting in this direction. Okay. Going from A to B. And its magnitude is mu n, which is mu mg cos theta, whereas the displacement is in the downward direction. Okay. So work done by friction will become minus mu mg cos theta into S. The change in kinetic energy is 0 because U is 0 here also and final V is 0 here also. Okay. Change in spring's potential energy is half K x square, where this x will be equal to 0.2 meters or 20 centimeters. And delta U will be minus mg h1, let's say, where here to here this height difference is h1. So we can see that this h1 is nothing but s sine theta. So that is 5 sine 37, or it is 3 meters. H1 is equal to 3 meters because S was 5 meters basically. So let's see what this equation is giving us. So M was how much? It was 2 kgs, right? Yeah, M was 2 kgs. So this will become minus mu into 20 into cos 37. Okay, theta remember is 37. So cos 37 is 4 by 5 into S, which is 5 meters, is equal to half k into unknown k into this, okay, minus 2 into 10 or 20 into h1, which we saw is 3. So we are getting this relation, that minus of 80 mu is equal to 0.02 k minus 60, or 60 is equal to 80 mu plus 0.02 k. That's our first equation. This equation we are getting from work energy theorem for the motion from A to B, which I've shown above. Okay, so make a note of this first. And now what we need is one more equation because we have two unknowns. So next what we'll see is as the block goes from this state B to, again it is rebounding. So as it rebounds, it reaches some other point C over here from where it had started from over here in B. So this displacement going from here to here is given to us as, say, S prime, that is given to us as 1 meter, because at C it again comes to rest. So next what we'll do is again we'll apply work energy theorem from B to C. Okay, so applying all these things we'll get another equation, and then solving these two equations we'll get the value of mu and we'll get the value of K. Okay, so note this down first, how we've got equation 1 by applying work energy theorem from A to B, and then come to this work energy theorem from B to C. Kunj, because see what is happening now, the block is starting from rest at A, and जहाँ पे मैं final state ले रहा हूँ ना, spring का maximum compression है, so the block has come to rest na against the spring. Momentarily it's come to rest before it rebounds. So the final speed is also 0 no. So both at my initial point A and at my final point B, the speeds of the block are 0. So the net change in kinetic energy is 0. In between the kinetic energy is increasing, but then again it's decreasing as it hits against the spring. Is it clear now? Okay. Yes, Uday, very good. You have done the calculation correctly. So now see, we have to just write the equation from B to C ना. So B to C में भी क्या हो रहा है? B पे initial velocity 0 है, C पे initial velocity 0 है. So the change in kinetic energy will again be 0. When we are going from B to C, work done by friction is change in kinetic energy plus change in gravitational potential energy plus change in spring's potential energy. So this time again, as you're going from B to C, your displacement is happening in the upward direction. Okay, whereas the friction is going to act down the inclined plane. So friction is still going to do negative work. Mu mg cos theta जो है, so this term will be minus mu mg cos theta but into s prime instead of s, because it's going through 1 meter. This term will again be 0 because again at C the speed is 0. Again at the starting point at B the speed was 0. Okay, but change in gravitational potential energy ये भी positive हो जाएगा. ये h prime है, so this will become plus mg h prime. And change in potential energy of the spring क्या हो जाएगा? Negative half k into x square, because by the time you go back to C, the spring has come back to natural length. And when the system is in the position C, the spring is back to natural length. Okay, so the final potential energy of the spring at C is 0, whereas the potential energy of the spring at B was half kx square. So this is for the spring. So this term, when we write it in equation, it will become minus of mu into 20 into 4 by 5, okay, into 1, because now the displacement is 1 meter in magnitude. This should be equal to 20 into h prime will become 1 into sine theta, so 3 by 5, okay, minus again that term 0.02 k. So ये इक्वेशन अपना ऐसा आ जाएगा, minus 16 mu, correct, is equal to 12 minus 0.02 k. So this will be our second equation. Is this correct with the same equation you have got? Okay, so now we can solve these two equations. Okay, very good. So solving these two equations, you will find the unknown quantities. So the spring constant will come out to be 1000, or यहाँ पे SI units में, so that means it is 1000 Newton per meter. K will come out to be 1000 and it will be SI unit. So that is the same thing as 10 newtons per centimeter. You can also write it that way. And the coefficient of friction will come out to be 0.5. Okay, so this is one of the very key questions to understand the application of work energy theorem in a system which has both gravity and spring potential energy. So most of the questions at JEE level are of this type in application, जहाँ पे gravitational potential energy भी use करना है, spring का potential energy formula भी use करना है, and there may or may not be work done by friction, like in this case. ठीक है? So a lot of applications are in this, and a lot of applications are also in vertical circular motion, which you would have done in the chapter of circular motion. Okay. So when we are the next lecture also, we'll be doing more questions and doubts. Okay. So during that time, we'll take up some questions from vertical circular motion, especially if you have doubts. All right. So that's it for today's session, people. Next week, the first lecture we will discuss will be this thing, more doubts and questions only. And later from there, we will move on to the next chapter. Okay, people. So that's it for today's session. Okay, wish you all the best. Hello.